Welcome to Chemistry 111. Today we're going to finish up Chapter 11, perhaps look at some Achieve homework from the 3 different sections. We will probably continue looking at some of the Achieve homework, so if you have Achieve open during the lecture, we can actually maybe knock some of those problems out for you. So keep that in mind. After that, we'll start reviewing for the test, and we'll probably have the test due in 2 weeks' time, like basically not this coming Saturday or Sunday, but the next coming Sunday. Once we've finished the reviewing for the test, pretty much what we're doing is trying to re-review and refresh all the material, because the last test, the final, which will be held in here, so we have to all show up for that. We're going to actually probably move it into the lab where we can actually hold 12 students. But we're going to take the final, and it's all multiple choice, but it's also cumulative over all the material. So there'll be naming things, there'll be 1 or 2 property of light questions. There'll be stuff about electron configuration and Lewis structures. So we'll have to refresh at least the basics of all that material for that. But in the meantime, let's go ahead and continue with our work. So we last finished up. We talked about the ideal gas law. We talked about how to use it. We talked about Dalton's law of partial pressures and how gases mix. And we talked about how to calculate density from the molar mass of a gas or molar mass from its density. We're moving on to where we actually try to look at the gases themselves, and we look at kinetic molecular theory of gases. So the kinetic molecular theory is the theory that explains the laws. This was proposed by Rudolf Clausius. And so some of these statements we've already kind of approached. These 5 major statements are the basis of this theory. These are the assumptions we have to make. 1, gases contain a large number of molecules and or atoms, and they're a continuous random motion. So remember that first slide we looked at, those atoms bouncing around in a box. Large number of atoms bouncing around like billiard balls. The total combined volume of all gas atoms, if you stacked atom to atom, is negligible, meaning almost nothing compared to the volume which they're contained. That's ideal gas statement number 1. We're assuming the atoms have no volume. Statement number 3, attractive and repulsive forces between the gases are negligible. So they're not collisional, but not the collisional forces. So when they bounce into each other, they bounce just like billiard balls on a frictionless plane. They're not attracted to each other like magnets. That's ideal gas statement number 2. We assume ideal gas has no volume and has no attractive or repulsive forces. So here's some new statements. So number 4, energy can be transferred via collisions, but the average kinetic energy of all molecules does not change with time. So these collisions transfer energy. So if a stopped billiard ball gets hit by a moving billiard ball, the moving billiard ball slows down, the stopped one starts moving, and the energy transferred, it's like energy is conserved. And then finally, the average kinetic energy is proportional to the temperature in Kelvin, regardless of what gas we're dealing with. So the only way to increase the kinetic energy in this system is to heat up the gases. Otherwise, the net kinetic energy is constant. So these statements we're going to use when we look at these gases. So, let's see. Okay, so what does this essentially do? It explains how the ideal gas law. Remember, we said pressure is a force. Pressure is a collisional force of a fast-moving gas particle against a wall. So Boyle's law says that at constant temperature, which means if all the energy in the system is constant, then the average number of collisions per minute within a certain is constant within a certain volume. If the volume were to increase, the speed is essentially staying the same, so the gases will have to travel farther per collision, and so pressure must decrease. As I said, Charles' law, when we increase the temperature, we increase the kinetic energy, and thus we increase the speed. At a higher energy, there should be more collisions, which means higher pressure. But in order to keep the collisions the same, we would have to increase the size, the volume of where the particles are bouncing around in. And finally, Avogadro's law. If the number of molecules increases, there should be more collisions. But so how do we do that? We increase the size to fit more gas particles in. It's essentially, we're explaining the three laws. I kind of already did this, but now we're taking a little bit more in-depth look at it. And in fact, we can look at energy distributions. The individual gas molecules are moving at different speeds based on the kinetic energy. That kinetic energy is equal to 1/2 mass times velocity squared. But not all gas molecules are moving at the same speed. We actually have a distribution curve of speeds depending on the temperature. The higher the peak, the more gas particles are moving at that speed. But at any given time, there's gas particles like almost at a standstill, and there's gas particles moving really, really fast, but the majority of them are somewhere in the middle. Well, what happens when I increase the temperature? Increase the temperature, we're seeing this curve shift over. So the kinetic energy increases, and we still get some slow gas particles, but we get more of them are moving faster. So the average has moved over, and more of them can reach even higher and higher speeds. And if you took the integral, we're not going to do an integral, but if you took the integral, which is the area under the curve, you would see the red curve has a higher kinetic energy, while the blue curve has a lower kinetic energy. So the area under this curve would be less. So we can look at this, that kinetic energy is equal to 3/2 R times T. And so we can actually calculate for this. But these energy distributions can be described on various different ways, but the main way we look at the velocity is the root mean square speed, which is essentially looking at a way of looking at the average velocity based on kinetic energy. So the kinetic energy of a gas will actually be dependent on its molar mass. Because if we take kinetic energy is equal to 1/2 mv squared, but kinetic energy is also proportional to temperature based on 3RT over 2 Avogadro's number. We get, if we move the mass and Avogadro's number to one side, to solve for velocity. And square root mass times Avogadro's number is going to give us our molar mass, the 3RT. And so we end up getting the root mean square velocity is square root of 3RT over molar mass. That essentially, if we know the temperature and we know the mass of a gas, the molar mass of a gas, we can know how fast it's moving on average. Please note the units. If velocity is in meters per second and R is going to be kilograms meters per second, moles, what, like, I can't really read that, it's kind of cut off the screen, but if it's kilograms meters squared per second squared moles Kelvin, That means the molar mass has to be in kilograms per mole to cancel everything out. But from this, you could figure out how fast on average a gas is going. What does that mean? Because we're dividing by molar mass, the lighter the gas is moving, the faster it's going to be moving on average. So hydrogen gas is going to be moving at a faster speed than, say, helium gas, which is going to be moving at a faster speed than, say, nitrogen or oxygen or fluorine. As we get heavier and heavier gases, to get the same kinetic energy, which is going to be related to the momentum, mass times velocity, you need heavier gases will be moving at a slower speed to have the same collisional force. So I will not test you over this, but there may be at least one problem on the homework. So there's going to be 3 times R, which is 8.314, times temperature in Kelvin over molar mass in kilograms per mole. But where are we going to actually use it? We're going to use this in a much easier way. As I said, because of this equation, gases that are light are going to be moving at a faster average speed. So what we see here on this graph is that the lighter gases have a wider ranges of speed. The heavier gases have a much narrower range of speeds because of this distribution, because they have to have the same kinetic energy. So we're going to look at the effusion and diffusion. Diffusion occurs when small concentrated volumes of gas expands and mixes with a larger gas. So if like there's a leak in a container, it expands, it's like a gas mixes with other gases, like how a fart travels through a room and spreads out. That's going to depend on both speed, but also the mean free path, meaning how much gas is currently in there. You have a lot of gas particles, it's going to take a lot of time to squeeze through. But little gas particles, it's going to diffuse really easily. Now, effusion is the main thing we will measure. Effusion is specifically the expansion of a gas through a small hole based on pressure differentials. So we have this top thing, a high pressure system. We have the bottom container, a low pressure system. And we look at how fast does the gas leak through that hole. This concept is the basic concept of why balloons will go flat over time. Balloon, despite it being a nice sealed container, is not perfectly free of all atomic level pinholes. Gases are bouncing around in a high pressure system. When they bump into those pinholes, we're getting atomic quantities of gas leaking out. And as they leak out, the balloon will slowly go flat over time until the pressure inside and outside have been equalized. So, and gas particles will hit that pinhole based on their speed. The faster the gases are ricocheting around, the more likely they're going to ricochet into that pinhole. It's just a sheer random bouncing around effect. But so to look at this, we're going to look at Graham's law. Graham's law says we're going to compare the rates of effusion of 2 gases. Gas on one side or there's gas on another, or 2 gases, how fast do they effuse with relation to each other? And they're going to effuse based on the comparison of the 2 molar masses. So we look at the rate 1 over rate 2 is the square root of molar mass 2 over molar mass 1. So where do we get that equation? That equation comes from, we take the velocity of 1 over the velocity of 2. Velocity of 1 is, remember, 3RT over molar mass. Velocity 2 is 3RT over molar mass. Well, if we're considering both things at the same temperature and R is the same, 3RT cancels out. And so you have 1 over molar mass 1 over 1 over molar mass 2. You change it from these improper fractions into a proper fraction, and you get the square root of molar mass 2 over molar mass 1, which is what we see right here. So basically, I can look at how fast this is going to leak out compared to another gas based on the 2 molar masses. Doesn't depend on pressure, doesn't depend on temperature, because we're assuming both things are the same. But this would be why if you had a helium balloon and an air balloon filled up to the same pressure, which one is going to go faster? It's going to be the helium balloon, because the molar mass of the helium balloon is much smaller than what is air. Air is essentially 28.9. It's mostly nitrogen. So best thing to do is to just try a quick problem or two. At 100 degrees C, what is the root mean square velocity of steam? And then how much faster will it effuse with respect to oxygen? So at 100 degrees Celsius, what is the speed of steam, which is gaseous water? And then how much faster would it effuse with relationship to oxygen? So to do that, let's jump to the main screen. So we got water, which is 18 grams per mole. You have the temperature, which is 100 degrees C. Our equation is 3 RT over molar mass. But for this specific problem, there's a couple issues we have to deal with. First, we have to turn temperature into Kelvin. 2, we have to turn grams per mole into kilograms per mole. There's going to be like one problem on the homework like this. And 3, our R is not our usual R. It's 8.314 joules per mole Kelvin, which is 8.314 kilogram meter squared per second squared mole Kelvin. We have to use this R so that kilograms and kilograms cancel out. Kelvin, Kelvin, mole and mole cancel out. And we're left with meter squared over second squared. When we square root those, meter squared over second squared goes to meters per second. So 3 times 8.314 times 373 divided by 0.018. All that square rooted. So first things first, I'm going to evaluate inside the square root. Always a safe bet to evaluate first, write it down, then square root. You could probably put it all in once, but we want to make sure we square root the top and the bottom, not just the top. And this is a big number. That is fine. It's a big number. We are talking about speeds of gases. Square root of 516,853.6 repeating. Now I'm going to square root that guy. So, sorry. Raise that the power square root. You square root that, you get 718.9 meters per second. Even though that's a big number, we're talking about gases. They are ricocheting like crazy. Now, if gases were big, we'd feel that horrible collision against our body, but because gases are really small, we don't feel that pressure too much. Now, that is our first answer. The second answer, what is the diffusion with respect to oxygen? So we're saying rate of water versus rate of oxygen, square root of the molar mass of oxygen or the molar mass of water, which literally is the square root of 32 over 18. We don't need the temperature. We don't need the velocity. We could calculate what is the velocity of oxygen and then divide the two. But we'll make it easier. We'll just say, what is the square root of 32 over 18? All right. Oxygen is 16, so 2 oxygens is 32. You get 1.3 repeating, 1.333. So what does that mean? That means if I have steam at 100 degrees and I have oxygen at 100 degrees, the steam is going to escape through any pinholes 1.3 times faster. So if oxygen is escaping at 1 per minute, steam is escaping, let's see, it would be 4 every 3 minutes instead of 3 every 3 minutes compared to oxygen. But 1.3 times faster. It's all a ratio. Most of these numbers, if I say how much faster will this go, the number should be greater than 1. Should be greater than 1. 1.3 means 133% faster. Well, 133% of the speed, not doubling the speed, but 1.3 times the speed. So you should almost always get a number greater than 1. So that's a big hint. Okay. 17. All right. Now the last topic involves real gases. So real gases. Remember, our ideal gas assumes that the molecules have no or almost no volume and no attractive forces. And this works pretty well at low pressures. At higher pressures, meaning like pressures above 10 atmospheres, we start to see some serious deviations. So we should see a straight line, and really it's more like it levels off. We lose some of the accuracy because essentially the size starts to matter and the attractive forces start to matter. At higher pressures, the gases are starting to bump into each other more and thus interact more. So gases will deviate based on what element they are and also based on the temperature. So besides the side considerations, we will also consider the intermolecular forces known as the van der Waals forces. So obviously the size will play an effect of how much volume they can actually bounce around in. But we actually see a reduction or increase in pressure based on the attractive or repulsive forces. So if this blue molecule is trying to bounce into this wall and these other lighter blue molecules are attracting it, we would be pulling the molecule back, slowing it down like you had weights on it. Those are the attractive forces. And because you have these weights slowing it down, it would have a lower collisional force or a lower pressure. If you had an increased repulsion, it would be like giving the atom a nitro boost, and thus would have greater collisional pressure. So depending on those attractive forces or repulsive forces, we'll see a change in pressure. So we get the van der Waals force. Discovered by Johannes van der Waals, it is essentially the sum of all the different types of attractive and repulsive forces. some of these forces we will get to next semester. But we don't need to know what forces are interacting at this time. We're just going to say they're all a van der Waals force. So he essentially modifies the ideal gas equation to fix for these problems. We get first pressure, instead of just pressure, it's pressure plus the moles squared times the attractive force over the volume squared. Basically, if there's more moles of gas, there's more attraction. But if there's more volume, there's less attraction. So this accounts for both volume and the moles of gas, but this whole part deals with the attractive force times volume minus NB. Now the NB is the taking into account the actual volume of the gases. N, you say the more moles times the actual size of the gas means how much of the actual volume does the molecules have to bounce around in. And then we leave N and RT by themselves, just uncorrected for. But so we have this, so we'd have to take these into account. But please note, if we were ever to use this equation, A and B would vary from gas to gas, and you could look them up. I think I put one of these problems on the homework, but I will not ask you an actual math problem about these on the test. This is a bit beyond what I'm going to need us to do. But the fact of the matter is, all it is, once again, we define everything we know, we solve for what we don't know. The only difference is now we have a few more variables, and it's a little bit messier of an equation to deal with. But so the last slide we'll look at is this practice slide. So how would the temperature of 2 moles of CO2 deviate from an ideal gas under 5 atmospheres and 3 liters? So the first thing we want to do is calculate how would this gas be under ideal conditions. So what would the temperature of this be? Meaning, if I kept this under this pressure, the gas is going to have to be at this temperature. So start by pulling the main screen. So ideal gas, PV equals nRT. Pressure is 5 atm. Volume is 3 liters. Moles are 2 moles. And R is 0.08206 atmosphere liters mole Kelvin. So, with that in mind, PV over nR equals T. Ideal gas is just 5 times 3 divided by our 2 divided by our R. So under ideal conditions, our temperature would be, that's not math I can just handily do in my head, unfortunately. (91.4). 91.4 Kelvin. Now, under similar conditions, for the non-ideal, we have to account for P plus N squared over V squared A. V minus NB equals nRT. So however you want to do this, A is, okay, 3.59. 3.59 liters squared per mole squared ATM. The reason for those units is so that I can add atmospheres to atmospheres. B is 0.0427 liters per mole. I'm going to calculate a new pressure and a new volume and then plug them into the ideal. But you could just as easily plug everything in and solve for T. Plug everything in. But let's look at what's P plus N squared B squared over times A. This is equal to 5 plus 2 squared, which is 4, over 3 squared, which is 9, times our 3.59. So our van der Waals pressure, is actually, instead of 5, it's actually 6.595 repeating ATM. And our volume is now volume minus NB, which is going to be 3 minus 2 times 0.0427. So 3 minus times 0.0427. So our actual volume is going to be 2.9146. So plugging that back in, 6.595, well, let's say 6 times 2.9146 divided by 2 divided by our R. Two. And what do we get for the temperature? The temperature is actually closer to 117.1. 117.1. It's 17.1. If I compare that to my ideal, shoot. Yeah. It is close to a % error. That's a 22% difference between the van der Waals and the ideal under these conditions. So, is this super important for everybody to use all the time? No. But, for example, if you're going into engineering, you're dealing with something where you have a high pressure steam pipe. This could be a big factor. You actually have to model a more effective law that will help deal with these deviations. You can't just say close enough when you're building a bridge. If you're a few inches to the left from where the bridge is supposed to, you're probably going to lose your job if the bridge doesn't collapse on you. You need to be a little bit more exact. And so some of these people actually have to account for these deviations that occur when you go in higher pressures. We're not even to 10 atmospheres. We just said, oh, hey, we're going to do this at 5. But it's still enough to make a big difference. So, but said. So we got 91.48, 117.1. And if you take the difference between those two, it's about 25. And you take 25 divided by 117 times 100, you get that 22% error. But as I said, you might be asked a question about the ideal gas equation, but I'm probably not going to ask you a math equation like that on the test. It's a bit much. But okay. So that is that. We'll start looking at some of the achieve homework now. We have a little bit of time. Okay, let's see. So we don't have these due just yet, but they'll come up, and it's the sooner we get working on them, the better off we will be. So we have 2 sets of stoichiometry, 1 set of thermochemistry, and 2 sets of gas ones. We'll go ahead and start with the gas ones just because we just finished this chapter. Looking at some of these. The gas ones aren't too much, though. There's not a whole lot of gas problems, even though it's split into 2 sections. One section is all the ideal gas stuff, and the other section is all everything else, pretty much. So, sorry, let me throw this. I'll throw this up on the screen in a minute. The first problem is just a simple conversion one. We're going to just practice our conversions between many different units. They'll give you the hints that that there's essentially 760 torr in an atmosphere. So with that in mind, let's see. So we have first 836 torr. So remember, if there's 760 torr in an atmosphere, 836, we're going to take 760 per 1. Okay, sorry, I'm blocking it. So we're setting that up. So torr ATM, because they're asking us to convert torr into atmospheres. So I'll do this just the top one and not, we'll look at maybe one more, but divide by 760. So that's 1.1. You may have slightly different numbers. Keep in mind. May have slightly different numbers. So don't just think you can copy down. So convert atmospheres to torr. Convert millimeters of mercury to atmospheres, and then convert torr to millimeters of mercury. So the last one's going to be the easiest one. Torr to millimeters of mercury. There's 1 torr for every 1 millimeter of mercury. So 760 torr is just going to be 760 millimeters of mercury. But we'll do that one. 24.5 atmospheres to torr. So we're just working way backwards. Once again, we start with what we're given. 24.5 ATM. For every 1 ATM, there's 760 torr. So we're just, so this one is going to be a really big number, because we're already, if 1 atmosphere is hefty, then 24.5 is going to be very powerful. So that's something like 18,260 torr. So it's going to be a pretty big number. But so looking at that, so that's just a conversion one. Then we have a series of questions that are going to be dealing with changing 2 of the ideal gas constants, 2 of the ideal gas variables, while keeping the rest constant, and asking for the unknown. So like a P1 V1 equals P2 V2 is this first example. So a pressure of a sample of argon gas was increased from 3.63 atmospheres to 8.47 atmospheres at a constant temperature. If the final volume is 16.3, what was the initial volume? We're going to assume ideal gas. So let's write down what we know. We say P1 is 3.63. P2, 8.47. Then they say the V2 is 16.3. So we just need to find out what is the initial volume. Careful reading tells us that this is the final volume, not the initial volume. So make sure you associate the P1 and the V1 with the P2 and the V2. PV equals P2 V2. We just need to make sure we put them in the right places. So 16.3 times 8.47. So 16.3 times 8.47 divided by our 3.63 puts us, the original volume would have been 38. The original volume would have been 3803 liters, or probably 38 liters. So as I said, you cannot copy the exact numbers. You probably will have slightly different numbers. But with that in mind, the problem is going to be set up almost the exact same. I want you to see this is not going to be hard if you can set this up. This is not going to be difficult if you understand what we're doing here. Just looking at it real quick, what was the hint for this problem? The hint might have been pressure and volume change, whereas that's a P1, we have a V1, final P2, V2. Yeah, so just looking at that. 5 mils of carbon dioxide were heated to 395. So if the volume of carbon dioxide at, let's see. Okay, so 30 people heated to 395. If the volume at the 395 is 600.8, what was the original temperature? So we have a volume initial, we have a volume final, we have a temperature final. The exact same setup, except the equation is slightly different. Instead of being directly proportional, these guys are, well, instead of being indirectly proportional, they are directly proportional. So your equation is instead V1 over T1, V2 over T2. And we need to solve for our T1. So how do we solve for our T1? We're going to have to get T1 to the other side and then isolate the T1. So what are the equation actually going to look like? When all said and done, we're going to have V1 over V2 times T2 equals T1. Because we have isolated the T1 from the bottom, we had to get it to the top. We don't want 1 over T1 as the answer. We want the actual temperature. So with that in mind, at this point, we've identified our volume, we identified our final volume, we identified our final temperature. We are just solving. I'm going to try to find time to run through maybe like at least set up 2 more problems. Let's look at this. Let's see. Might skip this one. Oh, but a bunch of, essentially, okay, that one I'm going to skip. You just have to put the Waals proportional, directly proportional, inversely proportional. So that's not bad. I'll look at these this one and the last one. We have an ideal gas, we have a pressure, we have a temperature, we have moles, and we're asked what is the volume. So this one, we're doing all the ideal gas variables all at once. So this is the PV equals nRT. PV RT. So we solve volume equals N R T for P. The only thing to note is that our R would have to be the 8206 because it's in atmospheres. But so 4.73. So we have what? 98.5 moles. 0.5 moles multiplied by our R, multiplied by our temperature, which is 449, divided by our pressure, which is 4.73. So I've just set it up, and we once again plugging them in and evaluate. Plugging them in and evaluate. What you have to do is just make sure everything is in the right units and you know what values you have. If you do that, you should be fine. So I'm getting the volume is something like 76.7 liters, which is a huge amount. But keep in mind, 98 moles of a gas. And it's not exactly at room temperature either. So 98 moles of a hot gas at a relatively low pressure means it's going to take up a big volume. And the last one is just the same problem. It's just the only difference here is Celsius. Make sure all your numbers get turned into Kelvin. Do not use Celsius. Celsius is not your friend in this one. The reasoning behind this is we cannot have a negative volume. We cannot have a negative pressure. If you had Celsius and we got down cold enough, you would go negative temperature, which would mean everything else turns negative. So we have to have Kelvin, which stops at 0. So that is just looking at a few brief problems from the gas law homework set 1. Hopefully you'll see it's not too intimidating. It's not too hard. All it is a series of essentially a series of ideal gas equations or ones like that. With that in mind, thank you for your time. And I will see you guys on Wednesday. We will continue where we left off, looking at some more homework.